I'm Dr. Janet Six, Senior Product Manager here at Tom Sawyer Software, and today we're going to be discussing how to build seamless collaboration in digital engineering. So first, we're going to discuss some of the needs for digital engineering and obstacles that are encountered while using this approach. And then we're going to discuss benefits of using graph technology in order to support digital engineering. And so I want to introduce our special guest speaker today, Liana Kiff. She is a senior consultant here at Tom Sawyer Software, and she has nearly 30 years of experience working with the design and control of complex systems, including for industrial control and building control and building portfolio management. In addition to the work that she has done here at Tom Sawyer Software, in the solutions department and working closely with our customers from several different industries. And so with that, I will hand over to Liana.
Sorry, thank you.
Yeah.
Hello, I'm delighted to be able to speak with you on this topic today. Go ahead, Janet, and start the presentation. 21st century digital engineering has really accelerated productivity in most fields of engineering in the last few years. And when it's working very well, you can really improve productivity and launch successful products. But when it's not working well, you have many sleepless nights and a lot of confusion. Digital engineering has advanced significantly from first transforming blueprints into digital drawings, but then further imbuing those drawings with meaning, and also tying those drawings of things to all of the other information in your product development environment that relates to that product, whether it comes from sales or it comes from services in the field or from the operations. You may have your own individual concerns about how to improve your digital engineering environment. Graph technology can help address many of these in making interactions between your different departments more smooth and addressing specific challenges that your engineering teams face. I'm not going to read all of these sentences aloud, but you might think about the concerns that you have. And if we don't address them during the presentation, you can ask those questions at the end. We're going to cover some of these topics in the following slides. So one of the first challenges with digital engineering is that engineering data is widely distributed. All of these departments that contribute to your product engineering environment are using their own tools, and those tools are very important. They're very specific to the kinds of concerns that those teams are working with, and yet they contain very important information that needs to be exchanged with other steps in the process, other teams using other tools. Graph technology is a really important tool to bridge these essential information resources and put them in the right context so that other people can use them. One of the big buzzwords that's come about to describe this is the term digital threads. Digital threads are designed to help you describe and orchestrate the ways in which these data need to be shared and processed and transformed in order to satisfy the different requirements of all of these different stakeholders in your product development. Digital threads track information over time across different use cases for that data and help to make those transformations of that data transparent and traceable. So digital threads help you to build more trust in the engineering data that you're sharing over time. And it also helps you to trace back and find out if you have a problem with your data, where is that problem happening? How can you improve it? How can you make sure that your data integrity over this vast collection of shared resources stays high? So one of the things I'd like to talk about is the notion of systems thinking. When we talk about any of the engineering domains, really, everything we're talking about is a system. And nearly everything that we invest in describing and modeling in detail is a system, and every system is a graph. Systems are generally collections of things that do something and then connect to another thing that does something else. And that connection represents something flowing between them, whether that's just a dependency in terms of a system graph, or if it's actually material that needs to flow from one place to another, or it's just information. All systems are graphs. All graphs, all edges tell you something important about how nodes in that system relate to each other, and perhaps how some physical thing or virtual thing is transferred between those two nodes. And this applies to every system out there, whether it's an IT network or it's a model of the cells in your body. This is what makes graphs, graph databases, and graph-based technologies, including visualization, so important in system engineering. And again, all things are systems, including business processes. Really big systems are often called digital twins. Digital twins are a virtual representation of a system or a system of systems that you want to use to communicate the status of a system and explore that system, perhaps. There are a wide variety of digital twins in terms of size and complexity. You may be familiar with some of the simplest digital twins. Some of the first ones that were really commercially accessible included things like your connected thermostat. Your connected thermostat shows you how it's behaving and how it's affecting your environment, at least in terms of one temperature, right? What is the current temperature now? Helps you to control that environment, set schedules. That's not a very high fidelity digital twin. It's also not a very complicated one. Some digital twins are as big as whole cities, where all the transportation is modeled, all the way down to the current status of every stoplight on every street corner. Other digital twins don't have that degree of fidelity. It all depends upon what you're trying to control and what kinds of actions you want to allow people to take on that digital twin to affect its behavior. The one thing that all digital twins have in common, however, is that they require a lot of data about physical things, data about services that connect those physical things, and data about what they're doing in real time. One of the things that is enabling digital twins to become more common and reach new levels of complexity are information standards and modeling standards that make it more repeatable to build and maintain digital twins. And graph technology is another thing that can help you to maintain standards compliance by making sure that you meet the requirements of different modeling paradigms. Some of the general modeling standards that you might be trying to use include SysML v1 or SysML v2, which are used by system engineers, UML, which is a more generic and common modeling standard, or possibly business process modeling notation, which is very helpful in many fields to model the kinds of processes you want your teams to follow. These are all different systems of modeling that are applied to the systems that you need to use. Some industries have their own modeling standards, and I've offered one example here, which is S88 batch processing. That's a little bit like business process modeling on steroids for making sure that things that plants that make ammonia don't blow up because something went wrong with the way that the process is being modeled or controlled. And then finally, there are information modeling standards that add meaning to the things that are being modeled. Just because you are using, say, SysML v2, for example, and describing that you have an engine and a drivetrain and wheels on a car, that doesn't mean that another system will actually know what a wheel is or what kind of engine you put in that car. That's where information modeling standards come in, and you can tie these methodologies together to make information that is truly transferable and machine interpretable, not just interpretable by the person who drew the model. One of these standards of description is called industry foundation classes. This is a description system for building information modeling that has been in the works for a couple of decades now, I believe, and was first published as an ISO standard in 2018. And what you see on the right side is a very high-level view, a view, by the way, that had to be manually created, along with all of the other narrative information that supports people who are trying to apply this model. I have some links here if you're interested in more information about IFC, or I'll be happy to share that later. We're next going to look at an ontology, which is a formal description language that was generated from this model, which was not originally an ontology. And ontologies have very formal language that allows you to make inferences about the things that are in the model. Ontologies deliver a lot of semantic knowledge about the things so that you know when you're talking about a wheel or an engine that everyone understands what a wheel and an engine really is. So the IFC ontology is quite large. There are many, probably hundreds of thousands of triples that describe the information in the ontology. Ontologies can be very complicated, but ontologies start with a class hierarchy, which can be hard to interpret as a tree. Here we see in a circular view that we can more readily understand how deep some of these things are, how many things are related in this subclass relationship, and where there are centers of information within this model. Here's a view where this model has been grouped so that you can look at one piece of the model at a time. Here we're looking at the HVAC elements. I understand some of the words on the screen might be difficult to see. But even in this model, as soon as we start to explore it a little more fully, we get a little bit of spaghetti here because this is a very large model with lots of connections. So when you're trying to do information modeling with ontologies like this, you need some additional tools. So next we're going to see what happens when we ditch these spaghetti views of this model and start looking more specifically at how the subclass hierarchy is arranged in those domains we saw earlier. So here we're looking at the flow controller, which is a damper or a valve, something that controls how things move. But when we click on type, we see, there's something a little odd about this model. And now I can provide yet another view using swim lanes to say, this is how these things relate to each other in the model. And it helps the person who's trying to apply the model to use it correctly. And further, we can link to the documentation for this model, which is helpful for an implementer but hard to navigate and understand without a big picture to show you how these things relate to each other. We just saw an example of graph-driven visualization, where we're looking at an ontology and we're trying to understand the whole and also individual parts. Graph visualization can speed up human comprehension of very important connections in systems, whether that's a system of description, which is what an ontology is, or if it's a system like a heating and ventilation unit on your rooftop. Graph-driven visualization or data-driven visualizations can make information about your systems more widely available to more stakeholders without draining your engineering resources. Because somebody has to, if you don't have a graph-driven or data-driven system, somebody has to draw those visualizations that people need. One of our customers conducted a study that determined that nearly 80% of an engineer's time can be spent just producing the visualizations that other people need. They're not really doing engineering, they're doing communication. And by automating some of the delivery of these illustrations that people are asking for, we can dramatically improve their productivity. Janet. So this customer noticed that they were able to get down to about to reduce the amount of time engineers spent on the task of delivering diagrams to people and get a huge boost in productivity so that engineers could do the things they were meant to be doing, the modeling and the analysis of a system, rather than spending so much time trying to communicate to other stakeholders. We've been talking about design time engineering, and people tend to think of engineering as entirely a design time task, but there's a lot of engineering that relates to runtime tasks as well. And here we see an example heating and ventilation system, which is typical in North America. It's on the rooftops of most commercial buildings. And this visualization was automatically derived from an information model that is informed by that IFC ontology we saw. So all of the things that you see on the screen that were described in the model are defined by that IFC ontology, not just what they are, but how they should connect to all the other things in that environment. And so you can use models like this to automatically generate diagrams of systems that can conform to end user expectations for that domain. This specific illustration roughly conforms to how an engineer would expect to see this information. And typically in systems like this one, all such diagrams like this for monitoring a system are manually produced for each individual unit that's been installed in a building. You can imagine that that can get very time-consuming and complicated and expensive. And it can actually be quite a large part of the expense of installing new systems in new buildings. So by enabling this kind of thing with graphs, we're really taking a lot of cost out of the installation process. We're making a system much more maintainable, because if you change something in the model, then the diagrams will automatically be changed as well. There are a lot of other things that graphs help you to do at runtime. So being able to interrogate a system and find out why something isn't the way it should be. If the temperature of the air coming out of this air handling system is incorrect, we can easily see the flow through the system, and we can easily understand what part of the system upstream might be impacting the temperature of the air coming out. Or if there is no air coming out, why Why is there no airflow? Which fan isn't operating? Is there a reason that fan isn't operating? Further, you can use simulations like this to look at what if scenarios, to go back and see history played out so you can understand what happened in a system. Things like that can be very important when you're studying very complex systems and very critical systems such as oil refineries or nuclear systems. There are a lot of ways in which graphs can support system analysis. I talked about looking at flows, which is in the lower right there, and being able to trace things upstream and downstream that can help a great deal with troubleshooting in environments where information or materials are flowing or not flowing and need to be flowing. Other kinds of analysis can help you to improve systems, to understand how systems are behaving, what groups of things relate to each other most in a system. That might be useful in a network analysis to understand where you might do something to improve bandwidth across a system. Social networks, of course, you can find out where the pivotal points in the social network are. And by the way, social networks don't have to be made of people. They can be made of devices. Path analysis and traversal analysis, again, can help you to optimize a system or troubleshoot why a system isn't working as well as it should. So there are many ways that graph tools can be applied to improve communication among people, to improve communication across teams, and to make sure that the information that you need to share about your digital engineering is getting to all the right places, and that that information is trusted and reliable. And that's the end of my part of the presentation. I'm going to hand it back to Janet to show you some demonstrations of how graphs and systems, how graph-based technology can support system design.
Thank you. Thank you, Liana. So we're going to go over a few examples, additional examples of how to use graph technology to support digital engineering efforts. The first one, we're going to look at Tom Sawyer SysML V2 Viewer. And so this product provides visualization and navigation of SysML V2 compliant models. So I have loaded here a model, and we can see the initial visualization here on the right side. So we can see this core part of the model with a hierarchical layout, which is going to show us flows and dependencies in the model. We also had the ability to provide a orthogonal layout. So you can see here with a click of a button, I was able to update the layout. There was no need to manually organize anything. The software took care of that layout for us automatically. And so as a user, you can choose which is the more appropriate layout to understand your model and also to communicate key findings to your stakeholders. Okay, so now let's take a closer look at this model. So I opened this model element tree, and we can see here on the left side the different model elements that are available. And we can peruse the elements just as we did here. We also can navigate the model through the tree. So we can open up the different subparts of the model here individually, or we can expand and see everything. We also have search capabilities. So I am going to type in clutch because we have a model here for vehicles, and we're going to select the clutch port. And so you can see here that we highlighted the clutch port both here in the tree view, and we have a synchronization. We also selected the same port here in the visualization as well. And likewise, I can search for an element over here in the drawing view. It will take us to that element in the drawing view as well. Okay, so now let me do a zoom fit. And we're going to apply a hierarchical layout. So again, we're going to see the flows and dependencies. Now, this layout is provided for us automatically, but if we want to update it a little bit, we can. So for example, I can take this drive shaft element and say, I would rather have it here. And then we apply an incremental layout, and it will clean up the drawing for us. Okay, we also have the ability to show flow in different directions. So right now we're looking at a top to bottom flow, but I can also change that to a left to right flow. And when I apply layout, then we'll have the different direction. All right, so now let's show the way to interactively load data. So I'm going to return to this top to bottom layout. And we are going to go over here to our model elements, and I'm going to search for the rear axle element here, the rear axle assembly. And here it is in the tree. And so I have the choice to interactively load elements into the system. So I can load the element on its own. I also can load the element with children or with all descendants, either with a tree or with a nested structure, depending on what it is that you need to do as you are studying your model. So I'm going to load all the element with all descendants as tree. And you can see how the visualization was automatically updated for us. And so we are going to zoom in to this rear axle assembly element. And we also have the ability to travel through the different edges. So I'm going to use our navigate links tool here because I want to find out where are we connected here? What is this edge representing? We're going from rear axle assembly to what? So I'm going to use this navigate links capability, and it's going to take us to that part. I can right click and it'll give me an option to follow, well, what's connected to that? And then I'll travel this edge to the next element. Okay, so I'm going to do a zoom fit. And we are going to go ahead and clear this diagram because we want to look at a different part of the model. So I will right click and I can say remove all elements. And we start with a blank canvas. And here I'm going to search for the vehicle one. Oops, let's see, I have a typo. Vehicle one. Going to go to that part. And again, we are going to load elements, but this time we're going to load with all descendants with nested relationships. So again, you get to choose how it is that you need to visualize and navigate through your model. So you can see more information about the SysML v2 viewer with our webinar on that topic. We also have videos available on our YouTube channel. And now I'm going to bring up a supply chain example. And we're going to load one of our supply chains. We have over here on the left side, we have a product tree that shows us different supply chains that we have available. Over here on the right side, we have drawing views. Here we're looking at a supply chain for a fountain pen. Down here, we have legend information in addition to details. And then down here, we have different tables that are showing us the different products and transport flows and product alternatives and so on. Okay, so by the way, if you're wondering about this application, this was built with Tom Sawyer Perspectives, which is an SDK and low-code development platform for graph visualization and analysis applications. We used it to create the supply chain example. We also used Perspectives to create the SysML v2 viewer that we were just looking at. Okay, so we can see here the different components that are used to create subparts and how the subparts come together in order to create this fountain pen. But let's say that we have a problem with one of our elements. So let's say that we have a problem with the brass element. So we can see down here in the bottom, the inspector that tells us who's making it, the production codes, how many elements are they producing, and so on. Let's say that there's a fire at this factory. And so they go from producing 1,000 elements to 0. And you can see when I updated that production value, how the visualization automatically updated. We have a problem here. Where do we have a problem? It tells us here in the red areas. And so we can, for example, if we want to know more information, we can do some nesting. We can nest by the location of these elements or the region. So let's go ahead and update the visualization to show us the location of these elements. So you can see that the elements now have this box around them, and the box tells us what factory is responsible for the production of these elements. And so you can see, for example, here that this factory is responsible for 3 elements, and this factory over here is responsible for 2 elements. And this factory is affected by that problem that we have with the brass. So having these nested structures can tell us more information about the supply chain. So for example, if we were sending several parts back and forth between 2 factories and spending a lot of time in transportation, we would see that here in the visualization because we would see some edges back and forth here between those different parent nodes representing the factories. Okay, so now we're looking at the problem here for a particular chain. And if we want to, we can also zoom in to just the problematic part of the chain as well and focus in there. Now we zoomed into the problem. But here in this application, we can also zoom out, show us where more of the problems are, show us more context. So we're going to go over to our location interaction visualization, and now we can see where the problems and which factories are we having the problems and which countries are affected by these problems. And so we can do and expand all of these nested drawings, which are showing us which factories, which countries, and you can see here we have several red elements, and that is showing us where all the problems are across all of the supply chains for our enterprise globally. Right, and in the few minutes that we have left here, going to go to one example, which shows us a little bit more about how to use analysis to support digital engineering. So here we are. We have a microwave network here, and I am going to zoom in to part of the layout just to show the level of detail. And this quality of this layout is part of what sets Tom Sawyer apart from our competition. You can see the very careful layout of the nodes and the edges, and we have the visualizations of the crossing jump overs. We have integrated edge labeling. We have these different colors, which were determined by the application to show us information like bandwidth used and other status qualities of our network. Okay, so we have a visualization here of our communications network, but we need to understand at a high level what is happening with this network. So I'm going to apply a clustering analysis. And so you can see here how the colors of those nodes changed. And so the nodes that have the same colors are more closely related to each other topologically. So this is a data-driven analysis. The graph is telling us which elements are more closely related to each other. Okay, so now we're going to take the results of this clustering analysis and we are going to do an abstraction. What is happening at a higher level in this communications network? So I'm going to come over here to the settings and we're going to group by cluster and I'm going to apply a new layout. So what we're doing is that we're taking all the nodes of the same cluster and we're putting them into their own nested drawing. Okay, so let's zoom in there. Okay, good. So we can still see all of the details that we had before. We have the automatic layout, we have the colors showing us which cluster, we can see fully all of the edges and all of the connections between the elements, even if they're in a different nested drawing. Okay, so now let's use this nested structure to show us high level what is happening in our network. So I'm going to say collapse all of the nested drawings. And so now we can see the superstructure of our network. We know that there are clusters that have more information about our network, but at a high level, we can see where all of the different communications are happening between parts of our network. And if we want, we can go in and we can explore a little bit more information. So let's find out more about this cluster. And I can say expand selected, and we can see the details of what's going on in this part of the network. I can open another one if I want to. So we'll expand that part of the network. Good. So now we can see both high level and low level details. So we can see the clusters, we can see the communications between them, but we're studying some of the details of what's happening in these clusters. And if we want, we can focus into a specific cluster. So here I want to see just what's going on in this particular cluster. So we took a look at the obstacles today that you have in digital engineering, and we talked about the benefits of using graph technology in order to help us address those challenges. We looked at some specific use cases with SysML v2 models, supply chains, and then we showed how to use analysis in order to support digital engineering. We have more information on our YouTube channel. If you want to see more information there, we have several videos on some of these topics. You also can go to our webpage, and we have a wealth of information there as well.